Successive refinement means you break your code down into smaller chunks, and you keep breaking it down until you get small enough chunks that you can work on and understand. Quality design means it's easy to debug, verify, and maintain. It's very easy to write bad software. Bad software means that if you try and look at your code in 12 months, you have no idea what it means.
Usually for me, it's where the last version was.
So functions and friends are basic small chunks of code, and making decisions is talking about if then else statements and while and for loops. Switches can be normally open or normally closed, and I did talk about switch debouncing, which I believe was covered last month here. LEDs, you can install them backwards and they don't work. And it can be useful to use flowcharts when you design, set up your software design and also your hardware design. Testing should be continuous. When you try and debug your application, you need to be careful not to be too intrusive. By that I mean the debug code itself does not cause the program to slow down. So one example is if you have an embedded system and you have a LCD screen attached to it, it can take as long as 50 microseconds to send a character to the screen. By that time, you could have done hundreds or thousands of instructions elsewhere in your program. So the mere act of writing a character to the screen may affect the timing of the entire program and throw your whole debugging off. Sysdig is a timer that's on all Cortex M chips. One debugging technique they talked about was using an array. So an array is a series of values normally stored in a variable. What you can do when you're debugging is, if you want to see what the first 20 values are of a certain variable, you can send them to an array, and when your program is finished, you can read the array back and see what the variables were. Or if you want to see, if you expect values in a certain range, you can say if they're outside that range, shove them in this array, and then do the same thing at the end of your program and see what they are. That is fairly minimally intrusive. Strings are a series of characters stored in an array. Functional debugging talks about steps. So in the Kyle program, in the debugger, you can step once, which normally executes one line of code. You can step over, which normally runs to the end of that routine. And then you can step out, which finishes this routine and exits. You can also set breakpoints so that your code runs to a certain point and then stops. You can then evaluate variables and see what the program is doing. On embedded systems, most of them allow you to change the frequency of the clock that they run at. So phase logic loop allows you to change how fast the program actually runs on the board. If you speed your program up, you consume more electricity and generate more heat. If you slow it down, obviously less electricity and less heat. So one of the goals is to try and make it run just fast enough to get everything you need done, completed in the time that you need, and not faster than that. Sysdig is a 24-bit value that continually decreases itself, it decorates itself. So you can set what the starting value is by setting a reload value which is 24 bits long. that is used to keep accurate timing on the embedded system, and you can also use it to set periodic interrupts. The system gets down to 0, it triggers off some actions, and then you can go do some other stuff. Structs in C are where you group variables of different types together in one data object.
Sorry, was that word struts?
Struts.
There's a C in the word,
Yeah, it's
S-T-R-U-C-T.
really struct.
And it's short for structures.
Oops.
Yeah,
Okay,
struct.
I'll fix that.
So struts without the C is another term of some kind of programming framework. That's why I was confused.
Oops, okay. This is an example of a finite state machine. This was a new concept for me. So, finite state machines show what we know or where we have been. This is an example of a vending machine. A vending machine has a limited number of functions it does. It receives coins. It generally coughs out items. So you can map that out to a finite state machine, and you then know what your system is doing. The lab we worked on for this one was a traffic light simulator. Using that demo, but we'll skip that. Stepper motors control how many partial rotations the shaft moves. How many partial rotations a shaft can move and which direction. So for example, inside a printer, you want to control how far a piece of paper moves and what direction and how fast. One problem with I/O devices is that hardware is usually a lot slower than software. This slide shows 3 different ways of dealing with interrupts. The first one's called blind cycle. So if you know that you have a function that it's going to take 3 seconds to execute, then flush it finishes processing, you can do a blind cycle and say every 5 seconds, go back and do a loop, and just assume that it's finished. The next one talks about a busy wait. So that is a constant loop that says, are you ready yet? Are you ready? Are you ready? Sort of like your kids when you go on vacation. Are we there yet? Are we there yet? The last one shows an interrupt, which is a hardware interrupt. That is like you're sitting at your workstation, working away, and someone taps you on the shoulder and says, here, I need you to work on this report. You stop what you're doing, you work on the report, and when you're finished, you get back to what you're doing. Talked about 2 different types of serial interfaces, a UART and SSI. The difference is how they use the clock and synchronize between themselves. Conversions talks about changing a binary number into ASCII and back again. Distributed systems is talking about when you have many embedded systems into each other. So it may not make sense to have all of your processing done in one little unit. It may be better to split them off into small sections and have them talk to each other. Nokia 5110 is the LCD interface. It's called SSR. An interrupt is an automatic transfer of software execution in response to a hardware event. The hardware event is called a trigger. So when the trigger happens, the software basically stops and services that event and then carries on. You want to make your interrupts as short as possible, and you don't want to have them in any busy wait loops. So if you had an interrupt in a busy wait loop, you could basically stall your program while the wait loop finished. Passing data between threads, between different interrupts can be difficult. One technique is you shove things into a buffer or into registers, and then you can share values. The nested vectored interrupt controller controls interrupts on the Cortex-Ms. Each interrupt has an interrupt service routine that is stored in a memory address. So I believe there's 256 different memory addresses that you have interrupts for. Edge-triggered interrupts. So let's say you had a value and it was running at 0. When it changed to a 1, we would call that a rising edge interrupt, and it could initiate an event. When it changed from a 1 to a 0, we would call that a falling edge, and it could trigger a different event. Sysdig is one way to generate periodic interrupts. We use that in one of the labs to generate waveforms. Pulse width modulation is a way to change the duty cycle to a motor. For example, if you have a motor that normally runs at 10,000 revolutions and you want to change it to run at 5,000, you could send a series of short pulses to it and it would effectively slow it down.
How many interrupts does this processor have that you have access to?
I don't know if we'll finish once.
More than just a couple.
Right.
One thing you say the interrupt table was
I think it was, yeah, it's, I can look it up, but yeah, it's fairly big. Well, relative. We mainly play with the Sysdig interrupts, so we didn't get into playing with other stuff. When you try and capture digital signals and convert them to analog, you have to be careful about how often you sample and the data range that you're going to accept. This is an example of an analog temperature signal that fluctuates. You might be able to see in the middle of the screen there's a wiggle that the digital sampling just missed completely.
So what's the lesson in that?
That's coming up.
Nyquist is your friend.
Nyquist, yes. So, there's a thing called Nyquist theorem which tells you how often you need to sample and how big your sampling needs to be. So, there was an interactive demo, but I don't know why it's working, so I can't show you. But there's a ratio of how often you need to sample to accurately represent what you're trying to capture. briefly talked about how stereo speakers using magnets generate sound by creating waves, sound waves. This is an example of a single tone. If you adjust the period, as in the tops of the waves and make them stretch them out or make them shorter, or if you change the loudness, as in how tall the waves are, you'll change the tone. That's an example of a 3-bed DAC, and for this particular example, it was close enough for the representation they wanted. Going from analog to digital, you have similar challenges. You need to be careful how often you sample and what range you want to keep. So you need to be aware of the change in values that is significant. So for temperature, if you want to measure every 1 degree Fahrenheit versus every 0.1 degree Fahrenheit, you need to know that beforehand.
For the DAC, did you have a separate chip for doing the DAC, or did you just use some ports and resistors to?
It was all on the board. Yeah, the board's capable of DAC. And
I see.
ADC. Yeah.
So the board supports.
Yes.
How many bits in the DAC and how fast can you drive it?
The one in the lab was 4 bits, but we go a lot more than that. I want to say about megabits. It was pretty fast. We weren't playing with that speed. But if this is an example of a digital and analog curve you're trying to represent, then the next slide will trip you up. If your analog signal changed, you would capture the same data points and you wouldn't know the analog signal changed. This is where the Nyquist theorem comes in, and you basically sample half, formula something like Fs equals 0 to 1/2 Fs. With a data acquisition and control system, an example could be your air conditioning system. The real world has a temperature, the room is a certain degrees, that gets fed into an analog interface, which happens to be a temperature probe, feeds that back to a microcontroller, then the microcontroller converts that to another signal and tells your heating unit to turn on, or your cooling unit to turn on. That action kicks up. Temperature is affected in the real world, and it's fed back to the temperature probe, and the cycle continues. The professors also have a course on robots, and they mentioned they had a robot car that they had, and for this robot, it drove along inside 2 wooden walls, and when it smacked into the left wall, a sensor was tripped, and it turned right. When it smacked into the right wall, the sensor was tripped and turned left.
Sort of like a drunk walking down an alleyway.
Right.
So there were any turns?
It did turn. It smacked into the wall and just wrecked itself, yeah. So the wall was sort of going along and then turned 45 degrees and then turned again. So it smacked into the walls and just,
So no 90-degree turns?
no,
It didn't do any mapping, did it?
no. No, this was pure sensor driven. They did have another example of one that walked along a line and that was 90-degree turns. Had a video of that. And that was showing, that one was talking about sensors that was detecting what was underneath it. And when it got too far off the line, one sensor went absent and it realized, oh, I'm too far off, let me correct myself. And it slowly veered itself back to the line and did self-correction. And then if it went too far off, completely off, it goes, whoops, I'll take a guess. I'll either go left or right. 50% take you back to my line. This was lab 15, and I didn't get time to finish this, so we didn't even get time to start this one. This was wrapping up and putting all the pieces together. The introduction to graphics covered things like how you actually send images to an LCD screen, clear a buffer, you set stuff in a buffer, and then you send it to the screen. That's what some students actually made, the Space Invaders game. And there's fun and games when the little Martians walk off the side of the screen. They've got to roll around and get to the other side of the screen and come back again.
They didn't go back and forth.
I think these ones wrapped around and then they came down, and it was fairly involved. And they gave you the editing software to change your icons. So you can mess around and put your icon. This was the new lab for this year, Internet of Things. What I didn't get to do this one either. This needed the booster pack, which is a wireless add-on. What this project did was it communicated to a weather server on the internet, and you typed in your area code or your city, and it would ask the weather server what the temperature was. So you had a local weather station. So this was a ton of work, like I mentioned, more than 20 hours a week. Great introduction to embedded systems. There were a few students on the forums asking, why would I bother doing this course when I just want to use the Arduino and Raspberry Pi? This was a lot more involved than those things. And one of the common answers was, if you need to get into the guts of the Raspberry Pi or Arduino, or you have a new sensor that no one's used before, with this type of knowledge, you have a fighting chance of being able to get to work. I do want to finish the last few labs, and like I mentioned at the start, a few of these things could be complete presentations.
How fast the run?
16 megahertz when it's slow, and 80 megahertz when it's fast.
So, now that you've had the course, what are some things that you think you can do that you want to try to do?
So there's a few projects I've been following. One is the Open Sprinkler project. Open Sprinkler. So I bought that board a few years ago and assembled it, and that's currently watering my garden. I need to flash that chip and upgrade the firmware and make some changes to it. So I think I can do that now. There's a project called like Open HVAC, where the intention of the project is this guy's going to write a controller, so you can actually have an open source air conditioning controller, and then you can control opening and closing certain valves on, and have one room hot during the day and cool it down at night type of thing. And there's another project I'm looking at that was on Instructables that created a popcorn coffee roaster. So that was an Arduino circuit, so I want to have a crack at that too.
Could you go back to the beginning and put up the URLs?
I checked that they do not allow people to register for that course anymore, unfortunately.
There's the book. Oops. That's the book. And I'll make these slides available, so I'll send them to me. Anything else?
Yeah, what would you do differently approaching this now that you've been through it
time. Probably just more time is the thing that got me.
Interaction with other students, do you think the forums would have helped you if you participated in that?
Well, I use the forum, but a study group would be useful as well. So if you had time to organise, say, right, Saturday afternoon from X time to Y time, we're going to sit here and do our work, then that would probably be useful as well, yes. But I don't know how hard that would be to coordinate.
Any idea of how the variant, it's 28,000 students, some 4,000 or 5,000 you said did at least one?
At least 4,000 did one thing, yeah.
So assume it's 4,000 students. Any idea of how many were lone wolves like you versus an interaction with other people?
No idea. They published stats early on, and a lot of the students were in the US and India, and then the rest of them were scattered around the world.
So what was the hardest thing to learn, like the most intellectually, like, wow, I've never done anything like this before? What was the most difficult thing to pick up?
The two things that were challenging were the finite state machine and that 4-bit DAC control. They both took a lot of time and took a while to figure out what the steps were.
Was the hard part actually cranking through the work? It took many hours to actually get it working, or was the concept just like really difficult?
Well, the finite state machine, I drew the graphs and figured out that this goes to there, and that wasn't too bad. With the DAC, it was more the fact that I thought it was going to be easy. I've already got a 3-bit one here, how hard can that be? So if I approached that as a actual problem that, like, let's forget about this and how might I approach it, that would have gone faster. So the fact that I tried to take shortcuts burned me on that one.
How did the debugging interface respond to interrupts? Did you simply put a plain breakpoint in an interrupt handler and just trap inside that without any?
Yes, you could. So the system timer is where we were playing with it. So you could put a breakpoint inside that and run. Yes.
How did they interface to the real world with the switches? You got a switch coming in. There must be some way to say, okay, at that time something, the switch gets pressed. That's not under program control. That's some asynchronous external event.
Like push a button, LED turns on.
Yeah. So how do you say push a button? You
That
know,
would
while you're
be-
running the debugger.
When you're running debugger.
In the Sims,
When you're
In the simulator, okay, so when you're playing with switches, that was either like PF0 or PF4, and you had to have them like read from. So in the debugger, there's a little console that pops up where you can actually specify push the switch, and you set that register, and from there it basically sets that flag and everything's set. So inside the debugger, there's an actual simulator that shows you switch 0 and switch 1, and you can click on it and affect it.
So there wasn't a way to script that and have a repeatable, at a certain time into the program, I want this switch signal to change by the call. You have to do it, you have to set a breakpoint, go 50,000 cycles, click the button on the GUI, and then start running again.
I'm sure you could program it, because it was a matter of just reading or writing to that port, so I'm sure you say up to 50,000 cycles, then you can do this thing.
But it's a simulator, so it's not your embedded code that's setting that signal. Right?
Yeah,
It's
your code
external.
comes out. So you write your code, and your code say, okay, read from port PF0,
Right.
or write from port PF1, then the LED on. So inside the code, you're actually messing with those effects say execute this long, and then go read the switch. Go read that value of that register.
They usually call that like a stimulus file where you have, like, I don't know much about Kyle, but on, Atmel Studio, that it does have some support for that, and being that that's free and the other is it's pretty expensive, right?
The full version is expensive, yeah.
Yeah, it'd be surprising if they, being
Okay,
a,
yeah.
does support
Usually
that.
time-based.
Well, there must be a way of doing it, because that's part of what professors did for the grading. They set the switch and they push buttons in the simulator, so there must be a way of doing it, yes.
The question I should have asked was, when you're single stepping in the debugger, how do you keep from immediately going into the systic handler? I mean, what am I trying to say? In the real world, if you're trying to debug something, you have to somehow disable interrupts, or with something like systic, you'll just go into the interrupt handler and then out, and you might execute one non-interrupt instruction and then go right back. That gets in your face real fast, and I was just curious whether or not they had a mechanism for disabling.
You can turn interrupts on and off, if that's what you're asking.
Did the debugger work on the real hardware? Or was it just for the simulated environment?
Yeah, it does work on real hardware, because, yes. You set another option, so in the debugger you tell it, are you using real hardware or are you using the simulator? And then you carry on, yes.
Do you think this approach, I mean, you obviously had enough self-discipline and were able to do enough self-study and self-learning, that you didn't need the one-on-one attention from professors and things like that. Do you think this is a thing, or is it like something that's kind of cool, but only a select set of people could make it to a course like that?
24,000 of them didn't do even one experiment.
Yeah. But
That's
even
not
then,
unusual.
that's not a representative sample. I mean, that's out of a group of people that sign up for the class.
Right.
And so, I guess the thing is, like, there's a lot of people that think that, here I'm sitting, hopefully people aren't going to throw me out of the room, but, education in the U.S. has to change, right? That the cost and the approach of universities has to meet this new online digital world. And I guess the question is, does this feel like this might be part of that new world order in education, or is this a novelty? Or a niche?
Probably part of the puzzle and part of the solution. I don't think it's going to be the full solution. So I heard a talk by, I think the head of edX on radio show once, and he was talking about the similar question, because the announcer was saying, well look, MOOCs are well and good, but your failure rate is pretty damn high. Your dropout rate's huge. And his comment was, well, there's a difference between the number of students that sign up for a course and the number of students that actually do any work in it. So apparently a lot of students just sign up for the course because it's click here, register. But the amount that actually do and complete week one of actual study is significantly lower. And of that group, I think he said something like 60% actually pass the course.
Wow.
So if you separate the numbers and drill into a bit more, then yes, it might work. But there's other models where you might have a MOOC running like this, but you might have a weekly session at NC State. You get a bunch of 20 people in the same area come together and they work on it together. That would be a slightly better model.
That sounds like a better model.
Right. But that's also hard to organize.
Without critical mass.
Right.
Question for the room, who else has taken the course online before? I know you have, who else have? So I think I'll almost pretty much speak for itself, and not It's not for everybody mentally, those who really want to learn, and wouldn't put time, that kind of effort into it, I think it's a reasonable thing to do. It will replace education, but it doesn't need to replace it, just needs to fill a niche.
It's kind of like, like, I work for IBM and they make us do a lot of online training. But it's like the difference between training and education. The stuff that we have to do online is relatively straightforward, read the thing, take a simple quiz, move on. This is actually learning difficult concepts, right? Some concepts that some people will grasp and others will struggle with. I guess that's the part where I'm wondering how it.
I think another key word, which is they make you take courses online.
Yeah,
This is something you sign because you want to.
Yeah, that's true.
If you want to do it, you have to put time into it.
Yeah,
If you do it, whatever, I could do it. That's true. It's what you put into it.
That's true.
The next
I
10
took
years,
4
we're
years
gonna have a
ago
bunch
in
of
robotics by the guy that taught at Stanford and worked on the Google car. And I enjoyed it. It was done very similar to this. Actually, he gave you an algorithm to write. You write an algorithm, and your car basically worked through this sort of issue you had to resolve. And it worked about it. It ran in a simulated environment. I couldn't see the data for an agent. I saw the results of my finish, and then passed or failed in that class. Not that specific assignments told what failed, what didn't fail, what didn't meet. I learned one new algorithm, and I was going to learn another one. I could read a book, Reading a book, actually putting time programming is way different. It allowed me to walk through and do programming on small pieces because of the kind of things that I in concrete. I liked it a lot.
About a dozen years ago, I took one of my first online class was a Java class from California. I just was miserable with it. I had to end up taking a class at community college because I needed to say, wait a minute, you mean such and such? Oh, okay, now I get it. I could never do that. I need to be able to ask somebody something.
Did anybody sign up for that Java
Doing
group on?
these things as a small group is really cool. In fact, just with one friend.
Yeah.
Because two things happen. You get that effect where you can help each other get past something. And also, you're thinking, oh, I need to get this done because otherwise I'm going to let this person down.
Or
bruise my
competition.
ego
Yeah, exactly.
or
Exactly.
whatever, right? And
But it's clear, Max, I mean, you did this on your own. You were obviously motivated, you made the time for it, and you were able to do it. And you had enough background that you were not completely like, oh, I really need someone else to fill that gap. But you had enough of that kind of thing to do that. So, it's all what makes the cool thing is there's 50 of these sorts of programs, edX and Coursera and Udacity and Khan Academy and whatever. There's thousands of these things that are all going to fail for the most part, but 10 of them will sort of work. And
I think with the Khan Academy, what's interesting is that they are finding out, they are by monitoring the students. They're able to find out when they reach a plateau, because the learning basically you learn, like progress, eventually you reach a plateau. And at that point, they find if they can detect that point, that's when they break the mentor, and the kids make progress much quicker. So I think that you went through the hard way in the sense that nobody was there to maybe address some of the moments where you feel like, oh, I'm stuck here.
Sure.
Somebody help me.
Right. Yeah. Many times it'd be great to go, hey, how the hell do I do this? And so for me, it was spending time on the Piazza forums and searching through code and trying to find out, okay, what the hell are they talking about here? Look for examples. And I made a few posts, like one of them I did was trying to understand how sysdig function worked. So I posted probably half a page of code, and this is my workings, and this is what I've done, and went through like 20 different steps, and the answer I've got is wrong. What on earth have I done wrong? And then an hour later, after I'd done that, it suddenly hit me, and like, oh, I know what I've done wrong. Change this thing here, and all of a sudden, I'm coming out like that.
But that was 12 seconds after you hit send.
Right. Yeah. Document the whole thing, and very detailed.
That's when you went out in your garden and started playing around. That's when you went to play in your garden.
so I want to make a shameless plug. I emailed on the mailing list that I was trying to put it on the mailing list. I'm Chris Speck, by the way.
You're that guy.
I'm that guy. So basically, I want to run. So I do this professionally and taught professionally at Purdue when I was in grad school. So I would like to run one of these, a similar sort of thing like this, so local. Like just grab a bunch of random people who have some background, basically this group, and other people like us. And I'd like to do something like this, very similar structure to this. I have my own ideas for how to do it, but, so if anyone's interested in that.
Yeah, I think
Make sure it runs on Linux.
But anyway, so I wanted to speak at the last meeting, I wasn't able to get to the last meeting, so.
Yeah, I think that's terrific, and we should, this is the perfect place to gather up interested parties and explore that.
I think you've got a lot of folks, you've got guys like me who know just barely enough to be dangerous and ask a few right questions, and then you've got guys like Paul and stuff like that. And so, yeah, you could do well here.
I've got a couple comments. First of all, congratulations. It takes tenacity, it takes resilience, it takes dedication to go through, the grind. But, as the saying goes, things won't happen or we're working for. Regarding, education, and is this the way? Google doesn't require people to have college degrees. And the reason they don't is because they program, and there's a lot of programmers who never had, college course or whatever, but they took the interest and, they did the non-glamorous thing, to go to grind through it and to amass the difference between understanding and proficiency. And I mean, it sounds to me like the amount of time that you took, and for all that you were learning from where you were coming from, was about as good as it was going to get from a realistic perspective. So, I'd be interested to hear what you have in mind for the course and what audience you're trying to address.
Yeah, I didn't mean to hijack this.
No.
This is exciting. So afterwards, I'd love to. Are you married? You have kids? How did you schedule this?
Understanding one. But I did ask permission beforehand. I said, I want to do this course. It's probably going to be 10, maybe 20 hours a week. It's going to be 16 weeks. I just said, yeah, sure.
Good for her.
Just like that, just to get there, there wasn't any like.
No, there wasn't any, it's going to cost you dinner every night or something.
It may not have cost you yet.
And the final interesting thought is that when Obama said that he was going to make $100 million available for people to take education classes in technology, it made me think about this kind of example that, whether you go to a class or all those people that sign up that didn't do anything, you got to have a lot of drive and you got to have a lot of interest to and, like many things, you can't just throw money at it. It's not going to fix it.
I work for iRobot, and I work for other chip companies and other companies. We've hired people who are, let's say, tangentially related to the technology industry, and they do, the Georgia Tech actually has a complete master's degree online that you can get a master's degree in computer science, and you get told that free. You don't get the certification. It's kind of like this class. You pay, but we've actually hired people at a couple companies I've worked at who have cranked through it all on their own and learned this stuff and demonstrate the mastery of it, and didn't have to pay Georgia Tech or anyone $20,000 a year, $40,000 a year, whatever it is.
Yeah, this is having a profound effect in some foreign countries. One course I took, I remember a big uproar right at the beginning of the course because there was some kind of a countrywide firewall that was keeping people in country X from taking the course. And when I saw, and I can't remember the name, but it was not a country that you would expect, folks to be taking part in. They were just up to their hips trying to take this course from Rice University. And it was like, wow, people out all over the place are tapping into this stuff. It could be pretty amazing to enable, although if you're in Iran buying something from DigiKey is a problem.
Yeah, but it's great that they have the whole simulation where you do a good chunk of it without having to get it from digikey.com.
Right, exactly. I mean, that, and that's the thing. I mean, they can leverage the simulation and get the proficiency where when they see the real hardware, they might be even more prepared because they've had to work through all of these issues without being able to just, oh, well, see the LED blinking.
I would just throw out, YouTube is an awesome resource nowadays, just in terms of if you're already somewhat proficient, you'll find someone that's done like an hour series on a particular subject, which if you already sort of know what you're doing, will get you up to speed really fast.
And the pause button works real nice.
Well, thank you, Craig.